I'm glad to announce our today's speaker. This is Maxim Grigoriev. You see the title, and well, it's exactly 7:20, so we can begin. Maxim, you are welcome.
Okay, Joseph, thank you very much for inviting. I'm always happy to speak here. Today I'll talk about some specific. Oh, the title is wrong. Yeah, interesting. Well, it doesn't make much sense, much difference. I use the title page from another version of this. So it's about application of these methods of gauge PDEs to theories with boundaries, and in particular to asymptotic symmetries. So let me say a few words on the background of this and motivation of this sort of studies. So in applications in physics, well, not only physics, I believe, but I'm more interested in this type of applications. We often meet theories on manifolds with boundaries. The very famous example which was attracting and still attracting substantial attention is so-called ADS-CFT correspondence, and more general term for this is holography. This is a non-trivial relation which relates gravity type theory living in an de Sitter space and conformal field theory living on the conformal boundary or asymptotic boundary of this space. And of course, it's a sophisticated quantum relation, but already at classical levels, there are many parallels. And in fact, there is a deep geometry underlying this relation. One of the very well-known example is a so-called construction of Pfefferman and Graham, which was developed initially to find conformal invariance out of remaining invariants, because conformal invariants are difficult to find, invariants of conformal geometry, while remaining invariants are known because essentially you build them out of curvature and its covariant derivatives. And they gave some sort of relation which looks like extension of conformal geometry to gravity type theory in certain ambient space, of which also de Sitter can be considered as a certain submanifold. At the same time, people are mostly interested in gauge theories because these are the theories which describe interactions in our world. And we know that as far as gauge theories are concerned, there is a first principle approach to these gauge theories, which is one of the names of it is Batalin-Vilkovisky formalism, because it's probably the most symmetric and elegant way to talk about gauge symmetries. It is based on graded geometry. Mathematically, one can say that Batalin-Vilkovisky formalism is something like usual Lagrangian formalism, but in the differential graded setup, so where everything is differential graded. And what is important, of course, if we are interested in local field theories, we need to keep track of locality of the underlying geometry. And for this, you need a specific version of this BV approach, which takes care of locality by formulating this BV in terms of jet bundles. at least in the basic version, which enhance it sufficiently and gives, for instance, the powerful approach of local heuristic homology, which usually encode interesting physical properties of the underlying theories. This BV approach can be extended explicitly to manifolds with boundaries. This is a research program pushed mostly by Cattaneo and collaborators. And when you include boundary in the game, you see that somehow you also at the same time describing Lagrangian Hamiltonian version of BV approach. And the reason, but this I'm not, it's closely related, but I'm not going to talk about specifically this, but I'll talk about an alternative version, which can be considered as that based on what's called the KZ version of Batalin-Minkowski formalism, or what is more, probably more, what is closer to the audience in this seminar. It's also, it can be also thought as a version of BV merged with invariant approach to partial differential equations. So somehow the idea is not to stay with Batalin-Minkowski on jet bundles, but to develop analog of Batalin-Minkowski formalism in invariant terms on generic manifolds, not necessarily jet bundles. For instance, there can be a on-shell version which corresponds to PDE in Vinogradov sense equipped with gauge symmetries. In this, when you start to do this, you quickly find that there is a good object which can be considered as a specific differential graded generalization of partial differential equation, and which we called at some stage gauge PDE, just to have a name. I'll talk about this, and actually this was also one of the reasons why this object attracted some attention, because it behaves quite well with respect to restrictions to submanifolds and to boundaries, and more generally to submanifolds. Because a pullback of gauge PDE to a submanifold is again a gauge PDE, and in this way you can systematically relate let's say theories on the bulk and on the boundary. So aim of this talk is to try to, well, it's of course all work in progress somehow. By the way, I forgot, although it was on first slide, I have to mention that it's mostly based on a relatively recent work with Mikhail Markov, but also early important contributions, including those with Xavier Bicard, Alexei Kotov, and Glenn Barnish are very relevant. But specifically this approach to asymptotic symmetries of gravity is in this recent work with Mikhail Markov. Okay, so the aim of this talk is to try to develop kind of full-scale graded geometry approach to gauge theories with boundaries and to their symmetries. And as I said, it's going to be based on this notion of gauge PDE. Let me here list list the approaches, ideas, and methods which are important for this. So first of all, it's geometry of PDE, as I mentioned, then covariant phase space approach, which is widely used in the context of these bulk boundary relations. Then there is approach developed by physicists, which parallels in a way the geometry of PDE approach. It's based on representing equations of motion as a free differential algebra. And this was developed, this goes under the name of unfolded approach or free differential algebra approach in supergravity. It originates from supergravity in physics. It also, what is also quite relevant is conformal geometry and tractor calculus, because If we have gravity theory living in the bulk, it is well known that what is induced under some general conditions, what is induced on the boundary is a conformal structure, not the Riemannian geometry structure. So conformal geometry is quite relevant, plus some additional ingredients, let's say it's versions of BV approach, and also ideas from Fedosov quantization are also quite useful in this framework. Okay, so let me try to vaguely explain what the idea is, although the idea is very simple if we are not dealing with sophisticated gauge theories, and I'm sure it's familiar to the audience. So this question one is going to ask is, suppose we are given with a local gauge theory, and suppose that our space-time has the structure of a certain space sigma times half line, so that the boundary of this space-time X is precisely sigma. So it's when this coordinate on R is set to 0, you get boundary. And one can naturally ask a question, what geometrical physical data is induced on sigma? And what is the kind of first principle and maximally invariant way to extract this data? Of course, this is not the most general situation. One can consider more general setup where you have generic submanifolds or low dimensional strata like corners, defects, etc. But we stick for simplicity to this simplified setup where we have just a boundary. Okay, let's start from the toy model. So suppose that we are given with ordinary differential equations, which do not have gauge symmetry, so they can be always written in a canonical form like this. In standard first order form, and we are in one dimension, so our boundary is just one point. And of course, in this example, it's obvious that the boundary data is just this phase space manifold M, where psi A are coordinates. So speaking in terms of geometry of PDE, we have finite dimensional equation manifold. It's a bundle over timeline, and its fiber is a phase space. Equations of motion, these equations are simply covariant constancy condition, while V is connection in this bundle. This VA is connection. So this is this equation connection form. So this is covariant constancy equation. If our equations are Lagrangian, if they're equivalent to Lagrangian, then this manifold gets a symplectic structure, and we end up with a Hamiltonian formalism. This is one of the ways to obtain Hamiltonian formalism from covariant perspective, from PDE geometry, and this parallels a little bit with what we the talk of Kostya Drushkov, which we heard a few weeks ago. So looking at this toy model example, which is kind of obvious, the message is that what one has to consider, the pullback of the equation, understood as a bundle, so in intrinsic terms, to the boundary. Then you get certain new equation, in this case in 0 dimension, which knows about possible initial data for our equations. For the moment, of course, we don't have any boundary conditions. The same logic stays if we go to higher dimensions. So as a toy model, let's consider PDE on a manifold with boundary. Again, we are not describing gauge symmetries for the moment, so it's kind of standard, all standard considerations. I'm sure they are well known to experts, but to tell the truth, I don't know where what to refer for this. So it is known, of course, to experts. So if we are given this PDE, we can write down. So PDE is a bundle of our space-time manifold equipped with a flat connection, which can equivalently be seen as a Cartan distribution, which is a horizontal distribution on this bundle, which is involutive. And solutions are sections which are covariantly constants. So here we have a condition that our section sigma is a solution. So it's just a covariant constancy equation. And this is precisely the invariant definition of PDE, not very general, but sufficiently general for our purposes at the moment. And it's also known, somewhat similar formulations are also known to physicists. In this case, we follow same logic. We just pull back our equation to the boundary, to sigma. It's a pullback bundle. Connection is also pulled back. It remains flat. So we get a new PDE, which is now PDE on the boundary. On the boundary sigma. And one can think of space of solutions to this PDE as a kind of phase space of the system. Strictly speaking, if you have a generic gauge theory, then this space is going to be this equation which you induce on the boundary is, if it's a good boundary, it's just it encodes constraints of the system. So it's not a full scale Hamiltonian formulation. It's already like constraint surface. Solutions are points of constraint surface, if this analogy is legitimate. Okay. So now we turn to these gauge PDEs because they are important, because this phenomena of asymptotic symmetries and what makes this story with boundary ADS-CFT correspondence interesting, etc., is because gauge fields are involved. So we need a formalism which properly takes gauge symmetries into account, but which at the same time is geometrical. And I believe that a good version of such a formalism is this formalism of gauge PDEs. So of course, I explained what this is some time ago in this seminar, but I'm sure people do not really remember details, so I have to quickly remind what this is. So the idea is very simple. If let's start with 0 dimensions, which corresponds that we don't have differential equations. We, roughly speaking, have only algebraic equations. So we are talking about, so if it were PDE, we would have been talking about just smooth manifolds with trivial Cartan distribution. But in the gauge case, we still have a certain structure of which encodes gauge symmetries and potentially which can also realize our equation as a submanifold through the Koszul-Tate type resolution. So what we ask for, we take gauge PD in 0 dimension to be just a Q manifold, which by definition is a Z-graded manifold. The degree I always call ghost, following physical physical tradition, not DEq. So there is one fundamental degree. There are some auxiliary degrees, but fundamental degree is called Ghost number traditionally, and I keep this tradition. So by definition, in 0 dimensions, gauge PD is just a Q manifold. And usually we require it to be equivalent. I'll describe what equivalence is to a non-negatively graded, because if there are substantially, if there are negative degrees which cannot be eliminated, this gives some difficulties with interpretation. Though I believe it's also an interesting case, but let's assume that we don't have non-trivial negative degrees, so you can always kind of equivalently eliminate them. The standard example, so what is Q manifold is just a manifold, graded manifold equipped with a homological vector field, the one which squares to 0. So this Q squares to 0. And the standard example of Q manifold is just a shifted tangent bundle over a smooth manifold X. And in this case, Q is just a de Rham differential, because functions on shifted tangent bundle can be identified with differential forms. On the algebra of differential forms, there is a degree and there is a differential, which is the de Rham differential. So we get a perfect example of a Q manifold. Of course, it's a kind of simple example, but there are more sophisticated ones. But let's try to interpret this gauge PD differently. Of course, because for the moment I said nothing. I said that this is just a particular case of Q manifold. It's a special Q manifold which is equivalent to a non-negatively graded one. But the data which we have is enough to define what are solutions. Solutions in this case are going to be points of our manifold. So these are 0 locus. By definition, solutions are 0 locus of Q field. And also, one can introduce the notion of gauge parameters. I'm here. So these are vector fields of degree -1. And once I have vector fields like this, I can form vector fields of vanishing degree just by taking commutator with Q. And I can check that such vector fields, they preserve the solutions. Because Q vanish at solutions, such a vector field is a symmetry. But because it is generated by Q itself, it's a gauge symmetry. I can give an example. For instance, if suppose that Q has the following structure: Ci, Ri alpha, DOD phi I. Suppose it's where Ri. So these are like R alpha. These guys. They are vector fields, and let them commute. Suppose which. So they define certain distribution because they commute. So shifts along these distributions are considered as symmetries. For instance, and degree of Ci is 1, and degree use cost.
I'm sorry. Ci or C alpha.
Oh, alpha. Yeah, thanks.
Alpha.
Yeah, sorry. Phi I is 0. So I have variables of degree 0 and 1. That's it. So everywhere, all points of my manifold are solutions, because Q vanishes everywhere on the body of my manifold, because C has degree 1. So C equals 0 gives me space of solutions, and solutions are points. So anyway, coordinates with a non-vanishing degree must vanish there. But what is gauge parameter? Generic gauge parameter look like this. So we need to form a vector field of degree -1. The only way to do it is to write something epsilon alpha d over dc alpha. Because C is of degree 1, so derivative takes 1 unit of degree, and epsilon are some numbers. of functions, doesn't matter. And then gauge transformation, commutator of Q with Y, is something like epsilon alpha R alpha. So this is a vector field along which belongs to the distribution generated by R alpha. That's why this distribution is called gauge distribution. So you see, even from such a finite dimensional object, you can, this is of course a toy model of BV formulation, but a non-Lagrangian version of it, because BV can't be like this. You need negative degree variables. But if you don't care about Lagrangian, you can consider BV, which is non-Lagrangian, where you don't have symplectic structure, but you just have a homological vector field. And in 0 dimension, this is precisely it. So we have a transformation generated by this distribution R, and this is a gauge transformation. So somehow the physical space, which is described by this Q manifold, is a quotient of the manifold with coordinates phi, by which is the body of our manifold, by the distribution generated by R. So it's functions on this quotient space are functions annihilated by R. So these are gauge invariant functions. That's what is a rationale behind this construction. But in general, of course, there can be variables of different degree. We can have negative degree and a piece in Q which corresponds to consultate a resolution of a certain submanifold. So it's quite a flexible construction. But if you want to relate this to what usual PDE is, in 0 dimension PDE is just a smooth manifold. It's the case where our Q manifold is equivalent to just a usual smooth manifold. So which means by a certain equivalence relation, you can just set Q to 0 and get rid of all variables of non-vanishing degree. Okay. And now we exactly get to the point of this equivalence of Q manifold. So the idea, which is best illustrated on local analysis, is that if our Q manifold, which is MQ, our Q manifold, which is MQ, factorizes into a product of two Q manifolds. Such one is n with a differential Qn, and another one which is of the form T1V, where V is a graded space seen as a graded manifold, and the de Rham differential there. The Q manifold of this type, where we have T1V and de Rham, is called contractible. Of course, due to Poincaré lemma, you only have constants in cogomology, and in whatever natural sense, it is contractible. It doesn't bring anything to cogomology. So it means that such a factor, T1V and de Rham differential there, can be dropped without spoiling equivalence. This is a notion of very naive notion of equivalence. There are much more flexible ones. But what is important is that it's a product not of just product of manifolds, but it's a product of Q manifolds, which means that it is the Q structure, the Q field is a product Q structure. So in natural coordinates originating from factors, it splits into a sum of two terms. One is a Q structure on manifold n, and another one is just the de Rham differential written in coordinates and of course understood in a graded sense. So somehow V are like, if you want V, these variables V alpha in some sense D on D of W alpha, but of course we don't use de Rham in this sense. we call basis differential forms by new letter. Okay, so this is an idea of equivalence, and using such an equivalence, one can find usually kind of a minimal Q manifold to eliminate as many coordinates as possible. And this is called minimal model of a Q manifold. And if a manifold is formal, then it is known that that minimal model exists, because in this case, formal Q manifold is the same as L infinity algebra, for which it is known that minimal model exists and is unique up to isomorphism. So if we restrict ourselves to formal Q manifolds, like kind of perturbative analysis from the point of view of underlying gauge theory, then we know that minimal model exists. In general, I am not aware of such a statement, because global geometry comes into the game and some other subtleties. So it's a good question. There is a simple geometric characterization of such variables WV which can be eliminated, which is very practical if you work in coordinates. So what you're looking for independent functions W, such that W and QW are again independent functions. Then the surface where you set them to 0 is of course a Q submanifold, because by construction Q is tangent to it, and this gives you, at least in formal case, it gives you a equivalent Q manifold. Of course, globally there can be some subtleties, but sometimes we are just interested in general structure, at least locally, forgetting about some global aspects. And this, of course, also gives a simple geometric picture of the concept known as homotopy transfer. For instance, when you go from L infinity algebra to its minimal model, the L infinity structure on the minimal model is called the homotopy transfer of the initial one. But in these geometrical terms, all this homotopy transfer amounts just to restriction of Q to a particular Q submanifold, because it's tangent, so you just compute your vector field in terms of coordinates on the surface, and you get formulas for homotopy transfer. And in physics, similar considerations are also known for some time, and they, in context of gauge theory, they go under the name of generalized auxiliary fields or contractible pairs. Okay, we need a useful definition. It's a definition of a Q bundle, which is just a bundle in the category of Q manifold. So both total space and base space are Q manifolds, and projection preserves the Q structure. So it means that if we consider composition of pi star with QM, so it's the same as QE times pi star, right? So it's compatibility between projection and the Q structure. And in general, so, although we are only talking about locally trivial bundles, as a Q bundle, it can perfectly be a locally non-trivial one, because Q structure in infinite dimensions, of course, in finite dimensions, you can prove that you can factorize them. In infinite dimensions, generic Q structure doesn't factorize into a product. So there can be a piece in Q structure which depends on the base somehow, which is kind of connection piece which you can't get rid of. Okay. So this notion of Q bundles allows to define a notion of equivalent reduction which is geometrical, which is not necessarily local. So we say that Q manifold NQ is an equivalent reduction of MQ if MQ is a locally trivial Q bundle over N with a contractible fiber, and there is a global Q section. So it means that locally you have this factorization, but globally not necessarily. And this corresponds to, and then you can prove that cogomology, for instance, is isomorphic under such a reduction, because we know that if we are in a vector bundle, then no cogomology comes from the fiber, right? And we require fiber to be contractible space. So essentially, it's a vector space. Okay, so and this notion can generate an equivalence relation for Q manifolds. And now we are ready to define what is gauge PDE. So gauge PDE is a Q bundle over T1X, where X is space-time. X is space-time. Space-time. So we consider bundle not over X, but it's convenient to consider bundle over like differential forms on X, which we think of as algebra of as shifted tangent bundle over space-time. Again, we require equivalence to non-negatively graded to avoid some pathological systems. And this Q if you introduce local coordinates where x and theta are coordinates on the base and psi on the fiber, then Q should have the following structure in this trivialization. It should have a Durham piece. This is just a Durham differential plus additional piece, which is vertical, and in general it depends on x theta. If by picking a different trivialization you can get rid of x and theta dependence here, it means that your bundle is locally trivial as a Q bundle, but in general you can't. Okay, but again, this is not very deep. You just call a bundle. But what is important that this definition is to be supplemented to the definition what are solutions and what are gauge symmetries, and in general higher gauge symmetries, because then you can interpret this data in terms of a gauge theory. And the definition of solution is that solutions are sections compatible with Q structure, so satisfying this relation. These are called Q sections. In coordinates, it looks like this. But of course, at first glance, it looks like it is just a condition that sigma is a covariantly constant section, but it's not so simple because strictly speaking, these are sections over T1X, not X, and everything is graded. So in particular, section is parameterized by a bunch of differential forms. If in the fiber you have coordinates of positive degree, so it's a tricky equation. It more in simple examples. The typical example of such an equation is like zero curvature equation. If, for instance, among psi's there are one variables of degree 1. Gauge parameters again are vertical vector fields of degree -1, so that combining them with taking commutator with Q defines a natural infinitesimal transformation of sections. I work in terms of a pullback. The variation of a pullback of a section is given by a composition of section with this commutator. And for instance, in this example of zero curvature equation, if you, for instance, if you take a fiber to be just a shifted Lie algebra, you will see that this with a fiber Q structure being Chevalier-Lindbergh differential this Lie algebra, then you will see that this equation is going to be Morar-Cartan equation, while unfortunately I don't have this example explicitly on my slide. While these gauge transformations are going to be standard gauge transformation, because for instance, y you can pick as epsilon alpha of x du dc alpha. This is a rather general form. And so this is interpreted as C alpha fiber coordinates of degree 1 and epsilon alpha usual Yang-Mills type gauge parameters. So more or less, I'm giving an example of Chern-Simons theory, non-Lagrangian Chern-Simons theory in this term, which is a very standard example. Of course, if higher degrees are present on top of gauge symmetries, we have higher gauge symmetries. So these are transformations which act on gauge parameters in such a way that gauge transformations are trivial associated. It doesn't change the gauge transformation. So you can define a tower of such guys, and they are sitting in higher degrees. So it's quite a flexible notion. And a notion of equivalence of Q manifolds extends to gauge PDEs. So more specifically, we call a sub GPDE, which means it's a sub-bundle of initial PDE such that Q is tangent to the sub-bundle. It is called an equivalent reduction. This E-twiddle is called an equivalent equivalent reduction if E is itself a Q bundle over its sub-bundle, but it's a Q bundle already in the category of bundles over T1X, and the fiber is contractible. What does it mean? It means that we have a projection. So of course we have an embedding. E-twiddle embeds into E, but we also have a projection. We have like P-twiddle, which sends E-twiddle to E. But of course, both of them are bundles over T1X. So there is a projection here to T1X, and there is a projection here. And this diagram should be commutative, so that this projection E-twiddle to E is compatible with a bundle structure, and the fiber of this bundle pi twiddle again should be contractible. It's a bit involved, but if you look at it in coordinates locally, again it's a very simple thing. So suppose we are given, suppose our coordinates in the fiber split like this. So these are base space coordinates, x and theta. Theta, let me remind you, is roughly speaking dx, but we don't think of the RAM differential in these terms because we are in graded language. And then our fiber coordinate splits into phi, w, and v, such that q acting on w gives v. So these are like contractible pairs, this w and v. And they are, again, coordinates. Then you can pick E-twiddle to be just a zero locus of w and v, which gives you locally contractible fiber, right? Because the space, the fiber is going to have coordinates w and v, and a q acting on w gives you v. So it's a contractible fiber. So this is a simple example of equivalent reduction. And technically, if you are not interested in global geometry, it's a very useful characterization of this equivalent reduction. You simply eliminate contractible pairs like this, and you know that at least locally, okay, there are some maybe other subtleties which I don't want to mention. At least locally, in usual cases, you get an equivalence. And this is again related to what it's not precisely, it's much more general concept than usual generalized auxiliary fields, but philosophically it's the same, and it originates from this old story. And these generalized auxiliary fields were introduced as auxiliary fields for BV, for Batalin-Wilkowski master action. Okay, here is our example. So it's a PDE, usual PDE. It's a particular case of gauge PDE. So suppose we are given with a fiber bundle E0 over space-time, space of independent variables, and let it be a PDE defined in geometrical way. So it means that it's equipped with a flat connection. So what we do, we pull it back, this bundle, to a bundle over T1X. So we have a projection, right? We have pi, I don't know, pi hat, which sends T1X to X, and we have a bundle over X, so we can pull it back by pi hat. We get a bundle over T1X. In coordinates, it just means that you treat your dx as additional coordinates, and you form Q you take Q to be a covariant differential. If you think of theta as dx, this is just a covariant differential induced by a connection on our bundle E naught. But you can think of this covariant differential as a homological vector field on E naught pulled back to T1x. So we get a Q bundle. If we check what solutions are there, of course, just covariantly constant sections. And there are no gauge transformations because all fiber coordinates have degree 0. So there can be no vertical vector field of negative degree, which we need to form a gauge parameter. So we are dealing with just usual PDE rephrased differently. Nothing special. Another example which explains that it is quite flexible. This approach is BV formulation at the level of equations of motion. So if we start with a fiber bundle whose fiber coordinates are fields, ghost antifields, for those who are familiar with BV, then you take E to be a jet bundle of this initial bundle and also pull it back to T1x. So roughly speaking, functions on this are horizontal forms on the jet bundle, and then you take Q, you take homological vector field Q structure to be a sum of horizontal differential dH, which is now just a homological vector field because dx is theta, and the BV differential S, which is evolutionary vector field, so they commute. That's why Q squares to 0. But what is important, you need to give 1 unit of Gauss degree to differential form, to base space differential forms, to theta mu's, because only then this Q becomes homogeneous with respect to Gauss degree. And one can prove that in fact such a system is, as a gauge PD, is equivalent to the BV formulation. It encodes initial BV formulation. It encodes same equations, same gauge symmetries, everything, but it's not a very trivial equivalence. So this justifies the notion that we can actually embed usual BV formalism at the level of equations of motion to this concept of gauge PD. So this concept is very flexible. Okay, and another example, which is more of the type which we're interested in, is Riemannian geometry, or if you want, physicists would call it off-shell general relativity, gravity. And this is an interesting example because it also shows that this concept of gauge PDE is useful in speaking of geometry, because somehow you can think of geometry. It's very difficult, of course, to define what is geometry in general, but if we have in mind some standard examples like Riemannian, conformal, symplectic, something, you can think of them as gauge theories or as gauge PDEs. In which sense? In the sense that, for instance, you can think of Riemannian metric as a solution to a certain gauge theory with trivial equations of motion, but with non-trivial gauge symmetries, which are diffeomorphisms. It's a very physical, of course, approach to geometry, but it turns out useful in certain situations. And because now we know a good language to speak about gauge theories, which is a very geometrical language of these gauge PDEs, let's consider Riemannian geometry as a gauge PDE. So what we do, we take a bundle, which is just these sections of this guy are metrics, and this is just a shifted tangent bundle. So we pick, these are base space coordinates, these are coordinates, or these are coordinates on jets of metric, and psi A originates from here. These are odd coordinates on shifted tangent bundle. These are not these dx's. we are talking about, it's not yet, it's different. This is Xi, and we take jets of this Xi as well. So we take jets of this bundle G. So these are coordinates on this jet space. And in a suitable trivialization, we can then form a Q structure like this. We can take the RAM differential, plus we can take gamma piece, vertical piece, which is mimics Lie derivative. So the idea is to interpret Xi as a ghost associated to parameter of infinitesimal diffeomorphism. So Xi is like a vector field for which we shifted the degree. And then this formula, this is just the Lie derivative written in terms of jets. But gamma also should act on Xi to produce the algebra of it's like a Chevalier-Lindbergh differential for algebra of formal vector fields, something like this. Anyway, it's enough to define gamma, because then you require that gamma is evolutionary, because we are dealing with a jet bundle, so we can say this. So it defines action of gamma on all coordinates, and it is vertical, so everything is done. Q is nilpotent. For the moment, it's just a naive reformulation, but it already points at certain homological technique. For instance, if you ask a question, what are cogomology of this Q, you get and consider cogomology of this Q in the space of local functions, you will find what's called a Riemannian invariance, right? Okay. For the moment, it was off-shell GR, but we can equally well consider certain non-trivial PDEs imposed on our metric. So in particular, we can pick a subbundle determined by infinite prolongation of Einstein equations. That's what they look like. And Q is tangent because Einstein equations are diffeomorphism invariant. Gamma is tangent to this surface. So you get a new GPDE, which is just this subbundle with a restricted Q. It's not any longer a jet bundle. It's a PDE with additional structure because it's a Einstein PDE as a PDE plus this jet bundle of this Xi's and gamma defined on their sum. Okay, and another example which is useful for what we are interested in is the certain equivalent reformulation of this off-shell gravity. So instead of doing equivalent reduction, let's do equivalent extension, which has a geometrical meaning. So what we do, we take the bundle, the same gauge PD which we had, which described Riemannian geometry, and add coordinate of the additional dependent variable omega, which we require to be positive and of degree 0, and additional coordinate of degree 1, which is lambda. And then we can extend our Q to a new bundle such that the initial gauge PD is going to be an equivalent reduction. So what we do, we add the following term to metric by asking metric to transform, roughly speaking, under transformations whose parameters are associated to costs lambda. And also we ask Q to act on omega again by shifts in a way. And these pieces are the same. Okay, and we again extended by requiring Q to be evolutionary. Then it's precisely the example of equivalent reduction. We can observe that if we consider omega minus 1 and its total derivatives and act with Q on it, we get, if we do computation, we get this term plus something more, which is triangular type, so it doesn't mix. But because omega is positive, we can divide by omega, which means that by doing this transformation, we can set omega equal 1 and all its jets to 0, and we can also set lambda equal 0 together with all its jets. So we are back, and Q is tangent to this surface, and we are back to this Q which we had here. So this is an example of extension. But now, if we look at this sector and forget about omega, we see that this is precisely the reformulation of conformal geometry as a gauge theory, right? Because we have diffeomorphisms with ghosts psi a, these are parameters of diffeomorphisms. We have ghosts lambda, which are associated to Weyl transformations, which transform infinitesimal transformation of the metric is to lambda GAB, right? And finite transformation is like G equal to omega squared. Let me write here small omega squared, like this. Don't want to introduce extra notation. So it's Weyl rescalings of the metric with omega, which is, oh, no, not a good idea, not a good idea. Let me use different notation because omega is a field for me now and I want it to be parameter. So let it be nevertheless lambda and here big lambda. And lambda is non-vanishing. Then such a transformation is known as conformal or Weyl transformation of the metric. And conformal geometry is when we identify metrics related not only by diffeomorphisms, but also by Weyl transformations. So instead of metric, we have an equivalence class of metrics, which are related by a multiple of by a factor of non-vanishing function. So you see there is a sector of conformal geometry which you get by introducing this extra field omega. Physicists call it compensator field because it allows us to introduce fake symmetries because there were no conformal symmetry in the game, but we introduced new field and we got this new symmetry. Okay, and how can we? Why this language of gauge PD is useful? Now we can use equivalence of gauge PDs to produce new forms of geometry. For instance, if we start with Riemannian geometry, we can observe that jets of Christoffel symbols. Of course, Christoffel symbols means certain expressions of jets of metric, which have the same form as Christoffel symbol, together with derivatives of psi ghosts, they form contractible pairs. And also metric form a contractible pair with a symmetric part of a first jet of this gauge parameter psi. Locally that's correct, but there can be some subtleties globally. So suppose we go ahead and we eliminate these contractible pairs. This is an exercise people did long ago, well, not in these terms, of course, but people did long ago when they were interested in computing local Beresty cogomology for gravity. And it is known that what you get, you eliminate all these variables, you get with something which is not a jet bundle any longer. It's like a certain PDE, but with fermionic variables. But among these degree 1 variables, you only have psi A, which originated from diffeomorphism parameters, and antisymmetric rho AB, which is like antisymmetric part of a first jet of these gauge parameters. And then in degree 0, you have a whole bunch of Riemann tensor and independent components of covariant derivatives of Riemann tensor. And then you can compute Q. It looks like this. So you see here that there is one relation which tells, which look pretty much like part of, you can think of psi as associated to translations in Poincare algebra and rho associated to rotation, to Lorentz transformations. Then you see that what I have here is a Chevalier-Lindbergh differential for Poincare algebra. But it's not Poincare algebra because there are other terms. Well, this is the case with cosmological constant. Let me erase it. It's not, otherwise it's confusing. But the relations are spoiled, so there is a curvature here. And then Q acts on curvature in a certain way, which is already difficult to compute, but it doesn't touch the degree 1 parts. There is a non-shell version. If Einstein equations are imposed, then you only have, instead of Riemann tensor, you only have Weil tensor, because Einstein is Ricci flat, so Ricci is gone. You only have Weil. But what is instructive is to look what are solutions to this gauge PDE, which is an equivalent reformulation of gauge PDE for Riemannian geometry. So let's introduce notations for, let's consider a section sigma. So it's parameterized by such a one form field, and we use the same notation for like this section acting on coordinates corresponding to Riemann tensor, and then we write down the equations of motion. And we see that these are precisely the Cartan structure equations of Riemannian geometry, right? So this tells us that the curvature in the sector of translation vanishes, so there is no torsion. And this tells us that the curvature of Lorentz connection is precisely the Riemann tensors. Of course, there are higher equations, but these are the important ones. And if we are on shell, for instance, if we replace here R with traceless Weil tensor, it's easy to see that the consequence of this equation is an Einstein equation, right? That because the trace part of the Lorentz curvature vanishes, which is precisely the Einstein equation. So you see, somehow when we adopt this language, we can easily go from the language of usual language of Riemannian geometry to Cartan language of Riemannian geometry. And in fact, the same happens if we discuss conformal geometry and more general geometries. And also another important remark that in order for this equivalence to work, in order to be able to play these games, it is crucial to take the total degree, which is Gauss degree plus form degree from the very beginning, because the transformations, the changes of the equivalence transformations which we employed to reach this, they were inhomogeneous. They didn't preserve just Gauss degree. You really combine Gauss with differential forms. So this is quite a unexpected step. But once you allow yourself to mix Gauss with differential forms, you easily see relations between Cartan language in geometry and metric language in geometry. And this also gives an example of a reduction, which takes us from equation determined in terms of jet bundle to a sub bundle, which is not a jet bundle any longer, but we still can work with it. We know what solutions are, what gauge transformations are, etc. Okay, now we finally get to submanifolds. That's what we need for boundaries. So suppose that we are given with a gauge PDE, and suppose that our space-time X contains a submanifold B. It can be a boundary or whatever. For the moment, we don't specify it. Then it's easy to observe that if we go to T1X, then T1B is naturally a submanifold in T1X, right? So T1 of a submanifold is a submanifold in T1X. In coordinates, it's very simple. Suppose in adapted coordinates, suppose it's codimension 1, it splits into x naught and xi, such that x naught equals 0 is B. Then, of course, you also have theta naught, theta I, and then T1B is singled out by this, right? And the restriction of a function to this submanifold is just a pullback of a differential form from X to B. So it's very natural. Also, in graded geometry terms, the standard statement that the RAM differential behaves well with respect to pullback means that dx is tangent to T1B, right? The RAM differential as a vector field is tangent to this submanifold, and that's why it behaves well with respect to pullback. Okay, now let we have suppose we have a gauge PDE for which this X is a space-time. So eq T1X. And then what we can do, because gauge PD is just a bundle over T1X, we can pull it back to any submanifold, and in particular we can pull it back to T1B. What we get is again a gauge PD, because the RAM part is tangent and the rest is vertical, so it doesn't it is not affected by this. So again, Q is tangent, so Q is tangent to this I star E understood as a submanifold in E. So we get a new gauge PDE. We use the same notation Q to denote the homological vector field, because it's just a restriction of initial Q and we don't want to use too many letters. Of course, the same logic applies to the situation when B is a boundary, because it's just a submanifold. But of course, for this we need to consider gauge PDE on the manifold with boundary. And if we consider this pullback, what does it describe? It kind of describes gauge theory of boundary values. So if it were a usual PDE, then we know that a pullback to boundary is like describes equations imposed on boundary values of our fields. But now, in addition to our fields, we also have gauge transformation. So we can see by doing in a compatible way, we pull back not only equations, but also gauge symmetries, gauge parameters, and all that. So we extract a new, we like get a boundary gauge theory out of a bulk gauge theory. Okay, this is an example which is again related, and historically maybe this is one of the important example to understand how it goes. If we consider specific gauge PD which describes a first-class constraint system, so we have a symplectic manifold M omega, and we have constraints also T alpha. And suppose the Hamiltonian is 0 to simplify life. Constraints T alpha, then we know that there is a constraint surface T alpha equal to 0, and there are gauge transformations which are generated by these vector fields, Hamiltonian vector fields whose Hamiltonians are T alpha, and this is Poisson bracket. Then we know that we can phrase it as a gauge PDE. We take Q like this, and this is precisely what is known as a Hamiltonian BRST formalism in this particular case where Hamiltonian is 0. And of course, this Q just describes for us equations that constraints are equal to 0, and the following dynamics, which is a gauge dynamics where lambda Lagrange multiplier. But if we just pull it back to time equals 0, let's say to the boundary, which is just 1 point, what we get is just a Hamiltonian phase space of this system, but of course in the sense of BRST formalism. So we get our phase space with coordinates z, our ghost c, and our ghost momenta p, together with a BRST charge omega. So we extract immediately Hamiltonian formulation out of Lagrangian formulation. But of course, all this is BV, if you want. So it's another example of going to boundary. And but of course, if we don't impose any non-trivial boundary conditions, all this story is not very interesting, because it's just about different formulation of the same system, of initial conditions for the system, or something like that. In reality, when people are studying theories with boundaries, the dynamics becomes non-trivial where certain conditions imposed on the boundary. And it turns out that you can also describe boundary conditions again in these GPD terms. So the boundary, if we have a theory with boundary, we have induced gauge PD on a boundary. And then we can ask that there are additional conditions, but these are not only additional equations, but these can be also equations for gauge parameters, because it's just a sub-bundle of our induced boundary PDE. So it encodes additional equations on fields and on gauge parameters and other possible gauge for gauge parameters, etc. So it's quite it's again quite a flexible concept. Of course, one has to be very careful, because it may happen that even if you go to a non-trivial boundary, non-trivial submanifold, sub-bundle of this GPD, it changes nothing. For instance, it can be an equivalent reduction. You can just take an equivalent reduction of your boundary PDE, pretend that it is boundary condition, but in fact, it's not a boundary condition. It brings nothing. And the idea to understand what's going on is that you go to the boundary, you find a gauge theory on the boundary, but in this gauge theory, you can gauge fix something. If there are gauge symmetries which are algebraic, and there is no non-trivial topology involved, what you can do, you can just eliminate these pure gauge degrees of freedom, which is equivalence of our gauge theories. So you just go to a different equivalent formulation of the same theory. This explains why non-trivial subbundle can corresponds to trivial boundary conditions. Okay. And now we are ready to give a definition of what is GPD with boundary. So it's a GPD EQ T1x on manifold, where X is a manifold with boundary. And then there is a sub GPD, sub bundle of the induced GPD on the boundary, which describes boundary conditions in a very abstract form, like boundary conditions for fields, gauge parameters, etc. So we can regard this EB as a GPD of boundary conditions. Again, we need to say what are solutions, what are gauge symmetries. So solution is a solution to our E, to the total, to the big one, which is required to be a solution whose restriction to the boundary should be a solution of a boundary. So it roughly it simply says that your solution should satisfy boundary conditions. But what is less trivial is that you also require your gauge parameters to preserve boundary condition. That's how boundary conditions act on affect gauge parameters. So let me recall you that that gauge parameter is a vertical vector field of degree -1, but now we require it to be tangent, so to preserve boundary conditions. So it means that through this you also impose boundary conditions on gauge parameters, and real gauge transformations are generated by gauge parameters, so by vector fields which respect boundary conditions. And this is precisely the source in this language of asymptotic symmetries, because what might happen is that there are symmetries which look like this, but whose parameter, which preserve boundary conditions, but whose parameters do not preserve boundary conditions on parameter. So the new symmetry emerge, and this is precisely what people call asymptotic symmetry, although there are different definitions and it's not always obvious how are they related to one another. So I need to say a few words about symmetries. So If we have a gauge PDE, there is of course a natural definition of symmetry. It's just a vector field of degree 0 which preserves the Q structure. So it preserves grading and it preserves the main structure Q, and we also ask it to be vertical to preserve bundle structure. More general versions are also possible. In fact, one can relax the condition of preserving of Gauss degrees. This is also a very interesting story, but let's don't get to this. And once we have such a vector field which commutes with Q, we can employ it to act on sections, right? You can take infinitesimal variation of a section to be just a composition of pullback by a section with this vector field. So in components, it reads like this. And if you take W to be commutator of Q with Y, you indeed gauge symmetries, which we defined before. But in general, there can be symmetries which are not of this form, and these are global symmetries. So global symmetries are cohomology of Q in the space of vector fields where Q act by commutator, by Lie derivative. One can check that, at least locally, I don't know global statements, one can compare this with the definition of symmetries, the usual standard definition of symmetries in BV formalism as a quotient of all symmetries by gauge symmetries, and then they coincide. So it's a good definition. And in the case of PDE with boundary, we need, in addition, our symmetry W to preserve boundary conditions, right? So this vector field W should be tangent to a subbundle of boundary conditions. And now we get to asymptotic symmetries. And as I already mentioned, there are different approaches. So it's not a very well developed. Well, people understand quite a lot in concrete situations, and there is a deep reasoning for this. But at a very abstract level, I'm not aware of a unique and the best definition, but a reasonable one, which is compatible with what is known in the literature in standard examples, is as follows. So we call asymptotic symmetry a symmetry of the form like this. So it would be gauge symmetry. So if Y satisfied boundary conditions, so preserved boundary equations, this would be a gauge symmetry, a trivial symmetry. But a symmetry of this type can preserve boundary conditions. So W can be tangent to EB, but Y, the gauge parameter, can be generic, does not necessarily preserve this EB. And in this case, so these are like gauge symmetries, which in the bulk they are gauge symmetries, but on the boundary, due to boundary conditions, they become physical symmetries because they are not any longer gauge, because their parameters do not preserve boundary conditions for parameters. And these are precisely asymptotic symmetries. Of course, asymptotic symmetries are form a subalgebra of all symmetries of the boundary equation, right? Because they are symmetries of the boundary equation. But in principle, there can be more symmetries, and it's a terminological issue if you want to call them asymptotic. But usually people, by asymptotic symmetries, people mean those gauge symmetries which become physical in the presence of boundary and in the presence of boundary condition. And this seemed to be a useful geometric characterization of them. Let me also mention that if we don't impose any boundary condition, so if we take EB to just a pullback of our initial equation to the boundary, then we don't get non-trivial asymptotic symmetries because any gauge parameter satisfies the conditions, just a vertical vector field, which means that asymptotic symmetries are tightly related to boundary conditions. And what all this has to do with the probably most interesting and physical situation of asymptotically of gravity in the asymptotically, what's called asymptotically simple space-time. That's the setup where people study are mostly interested in asymptotic symmetries. For instance, in the asymptotically, so-called asymptotically flat gravity, people invented long ago this Bondi-Metzner-Sachs algebra of symmetries, which is a certain infinite dimensional extension of Poincare, and which is believed to play a role in our real world. In gravity, it's like a symmetry of gravitons in some sense, whatever. So this is a definition of asymptotically simple spacetime, which was given by Penrose. So suppose this is a definition of what's called conformals, of what's called conformal boundary. So if you have a spacetime X twiddle with a metric G twiddle, is called asymptotically simple. If there is another spacetime with boundary, X twiddle is without boundary. Think of it as a, I don't know, Minkowski space, but with tricky metric. Together with the function omega, which is positive, such that X twiddle can be identified with an interior of X. In the interior, the physical metric G twiddle is related to G by a conformal transformation. Let me remind you that in the interior, omega is positive, but omega vanishes on the boundary, and it's positive in the interior, plus some technical conditions which I don't have time to discuss. So this precisely corresponds to the picture that we take our space-time X twiddle and map it into the interior of a manifold with boundary, but in such a way that a conformal transformation of our metric G twiddle is well defined on the boundary. In this way, our metric G induces a conformal structure on the boundary, not a Riemannian structure, because of course this G is defined up to again conformal factor, so it induces a conformal structure on the boundary. And in addition, if our physical metric is required to satisfy Einstein equation near the boundary, then we say that our space-time is asymptotically flat or de Sitter or anti-de Sitter, depending on value of the cosmological constant lambda. So as I already mentioned, this data, this is called conformal boundary. So we take asymptotic boundary we map it to a boundary, to a finite boundary. So we map our spacetime to a manifold with boundaries, and on the boundary we get a conformal structure. This explains how conformal geometry gets in the game on when we consider boundary asymptotically gravity on asymptotically simple spaces. Let me remind you how do we look at it from gauge theory perspective. It means that, so what is xg? Xg is a metric, it's a particular solution of a gauge theory, because gravity is a gauge theory on a manifold with boundary. And this induces the boundary structure. But in fact, we now have all ingredients to describe this situation, to describe gravity on this manifold with boundary. So we introduce G and omega as fields. We require that omega, these are boundary conditions, vanish on the boundary, together with some additional conditions, and we require some non-degeneracy. So this gives us field theoretical realization of the asymptotically flat space-time, which we can now rephrase as a gauge PDE, which we already met. This sector is a sector of conformal geometry, and this is an additional sector. If we, in the interior, where omega is positive, we can use this last relation to eliminate omega, to set omega to 1, for instance, and eliminate the parameter of Weyl transformation and get back the usual gravity. But if boundary is present, and because omega vanish on the boundary, we can't do it. So this theory is not any longer equivalent, but it is a gauge PDE on manifolds with boundary. It's also a well-known, interesting observation coming from conformal geometry that Einstein equations on a physical metric Z-twiddle, prolonged equations, can be written like this. As an equation f equals 0, FBC equals 0, where FBC is the following expression. And this equation is well known as almost Einstein equation, because specifically, Einstein equations, conformal Einstein equations, arise as conditions for this equation to have non-vanishing solution omega. Somehow this equation tells you that there is a non-vanishing function omega such that if you multiply your metric by this function omega, it satisfies Einstein equation. And this is equation of a finite type. It's and considered as a subbundle in the second jets of omega. It precisely gives what is called, it's one of the definition of invariant definition of the tractor bundle. So we now see the structures of conformal geometry, and these structures encode our Einstein theory on the manifold with boundary. But this Einstein theory on the manifold with boundary is already prepared by doing this trick with introducing additional field omega. It's already prepared to be pulled back to the boundary, because this metric G is no longer singular due to conformal transformation. So there is a well-defined boundary structure. Okay, and so I need to hurry up, and I don't have. It's almost impossible to give all details of the derivation. So what we did, we actually checked that in this approach you can really derive this boundary structure for Einstein gravity in the case of asymptotically flat and asymptotically de Sitter, anti-de Sitter situation, and we confirmed that asymptotic symmetries can be derived in this way, and we confirmed the standard results in this approach. But also it has, of course, this approach has additional benefits because you can consider much more general situations. Let me sketch how you can get asymptotic symmetries in the interesting situation. So you pull back your system to the boundary, you obtain boundary PDE. Now you study it. Asymptotic symmetries are properties of this boundary PDE. To compute, it's convenient to go to minimal model to eliminate maximal amount of contractible variables to find a minimal model of this geometry which is induced on the boundary. Then if you are in asymptotically flat setup, which is mostly interesting from physics, from the perspective of physics, you impose additional boundary conditions, which are due to Bondi-Metzner-Sachs, these gentlemen's, and so you really have subbundles, so which gives you have a GPD of boundary conditions, and this gives you asymptotic symmetries. You can compute it and you can find it that it indeed in the standard setup this new approach, invariant approach, reproduces the standard BMS symmetries. What is important that on the way you also use the minimal model of conformal geometry, which is also known in the literature, which gives a Cartan formulation of conformal geometry, and this makes an explicit link with the approach to these asymptotic symmetries based on tractor calculus and conformal geometry. But it looks like this GPD approach is more general because you can apply it not only to gravity, but to whatever you like. So let me give you a few details. That's what a minimal model look like in the case of asymptotically flat gravity. You see again that all these variables, which are in the left-hand side, this psi, rho, lambda, c, etc., these are all of degree 1, and they correspond to Poincaré algebra. But Poincaré algebra look very strange on the boundary in this case, because the boundary has a structure of a sphere in 4 dimension, sphere S2 times 1 line. That's what you get at null infinity in the asymptotically flat space. So on sphere S2, you have a conformal algebra of S2, which is actually Lorentz algebra. And you see it in blue here. This is Lorentz. It appears as a conformal algebra on the 2-sphere, but then you also have additional generators. These are translations, which are realized in a very, very strange way. That's what makes this geometry on the null infinity interesting. It's not just a usual conformal geometry like in ADS-CFT or in Pfefferman-Graham, but you systematically get it from first principles by pulling back by pulling back GPD describing gravity to this asymptotic boundary. And already there, for this system, you can impose BMS boundary condition, which essentially sets your frame field to particular geometry, particular simple geometry, and then you can find that your asymptotic symmetry is indeed BMS symmetries, which contain Poincare, because naive expectation is that you have, because you fixed your geometry in a way, so you expect just to get residual symmetries which is Poincare or smaller, just killings on the killing symmetries on the boundary, but in fact you get infinite dimensional symmetry, which has to do with the fact that the boundary is null, and it is parameterized by these BMS transformations, which contain the specific part, which oh, sorry, it's not this, it's this one. This BMS transformation contains this specific part parameterized by generic function on the sphere via coordinates on the two sphere, but acting along this additional direction u. So it's infinite dimensional space. These are so-called super translations from BMS algebra. So indeed, it turns out that you can naturally recover these asymptotic symmetries in this GPD approach. But of course, you can do more, because we can work with whatever gauge theory. We are not stuck to gravity. So for instance, we can consider certain equation for matter fields which are coupled to gravity. So some fields phi, extend Q to act on them. Also introduce conformal weight W for these fields, how they transform under this fake Weil symmetry, and then induce system on the boundary. And this is a kind of very general version of what's called Pfefferman-Graham type. Pfefferman-Graham type procedure, which allows to, in Pfefferman-Graham is known in conformal, in our terminology, in asymptotically ADS situation, where you induce non-trivial conformal invariants, and in particular conformal invariant equations, from some Riemannian invariants, diffeomorphism invariant equations coupled to metric in the bulk. So that's the essence of this Pfefferman-Graham approach. Of course, there are various versions of it. A very similar version, which can be considered as a kind of predecessor of this approach, I developed with colleague Xavier Bicard for describing conformal invariant equations in a flat situation. And it turned out that apparently the best way to describe very general conformal invariant gauge equations is precisely this one. But it's more or less the same story, but less general and formulated in different language, so it's difficult to make an explicit link. But anyway, the message is, if you have a gauge, for instance, a matter field coupled to your gravity in the bulk, which means that in addition to gravity, you have, say, some certain equation like nabla squared phi plus m squared phi, like a scalar field coupled to gravity, you can systematically choose weight for it. Of course, something interesting happens only for specific Weil weights. You can systematically pull it back together with gravity to the boundary to obtain equations which are going to be conformal invariant in the case of asymptotically ADS situation, or which are going to be invariant in the sense of this tricky geometry. Sometimes it's called Carolian, curved Carolian geometry. You can obtain invariant equations. So it's kind of procedure to generate also quite a non-trivial invariant objects. Okay, for instance, just to illustrate, actually I already said almost everything which is on this slide. For instance, in the setup where cosmological asymptotically ADS, where cosmological constant is negative, and if you pick this weight, you can see the scalar field, you pick this weight to be dimension to this very well-known value of a conform, which signals conformal invariance, you precisely get equation which is a conformally coupled Laplacian on the boundary. If you change weight, for instance, if you, instead of L1 you put here L, where L is integer, like 1, 2, 3, etc. There is upper bound depending on dimension. You get what is called GGMS operators. These are non-trivial conformal operators whose principal symbol starts with box to some power L plus more curvature dependent terms. So this is of course well known in different approaches, but you can redo it in this one. And it's kind of more first principle derivation compared to what is known. I'm not sure I have time. I think I exhausted my time by far. I wanted also to mention that you can extend to some extent to Lagrangian series to check whether this definition of asymptotic symmetries is compatible to the definition of asymptotic symmetries in Lagrangian setup, where these are gauge-like symmetries which correspond to non-vanishing charges. But I think I should skip it, and because it's already quite late. So these are my these are my conclusions, also confusions. So it's not completely a mistake because many things are still confusing. So this is very geometrical in the sense of geometry of PDE, a version of covariant phase space formalism, combined with, of course, this BV-BRST formalism. It has been shown to be quite instrumental in the study of asymptotic symmetries of gravity and in studying invariant equations, etc. It kind of unifies if you put symplectic structure in, presymplectic structure in, it kind of unifies Lagrangian and Hamiltonian setup and relates to covariant Hamiltonian formalism. It also, in the case of gravity, it also gives kind of first principle derivation of tractor calculus approach to asymptotic symmetries, or something which is known under the name of conformal boundary calculus, developed by Gover and Waldron, using tractor calculus. And this also gives a field theoretical realization in terms of, I would say rather gauge field theoretical realization of Pfefferman-Graham-like construction, and gives its Carolian analog. Carolian means where cosmological constant is 0 and we are speaking about null infinity. The simplified version of the same approach gives a very powerful machinery to describe conformal equations for higher rank tensors, so-called conformal higher spin fields, which are also gauge fields, and they're quite involved, but this gives a good machinery. And we are looking forward to some applications in the case of, which is very popular now, the so-called flat space holography, whose idea is to find a duality between physics in four-dimensional space and, let's say, physics in null infinity. Okay, so thank you. I think I'm done. Thank you very much.
For the moment, Joseph lost internet a few minutes ago. So I will substitute him. And so the question is, are there questions or remarks?
Yeah, looks like it was too much physics talk.
Okay, so no, but this was very interesting. form of matricials at least.
Kostya is saying that he has some problems with microphone.
Yes, but he has from the very beginning.
Okay.
Okay, so thank you very much. And
Thank you for attention.
Can you send me your slides for the site?
Okay, fine. I'll just change title because it's more or less the same, but it's better that it identical to what I announced. Okay.
Okay, thank you.
Thank you. Bye.
So thank you and bye. Thank you to everybody.